You ever felt that sinking feeling when you realize the world's energy and technology race is moving faster than you can keep up? Imagine waking up to headlines about a new semiconductor embargo or a sudden spike in lithium prices and thinking, how does this affect me? What does it mean when the largest cobalt mine in the Congo is owned by a company based halfway across the world? How can a single policy change in Brussels ripple through power grids in Texas and data centers in Silicon Valley that frustration millions share as governments and corporations jockey for control over resources, and innovation can feel overwhelming? Yet, what if you could trace the threads connecting renewable energy transitions, rare earth magnets, digital infrastructure, defense technologies, and emerging industries all at once, and understand how each decision shapes your everyday life? Today we are diving into the heart of global geopolitics, where every election, trade agreement, and investment decision sends shockwaves across continents and into the devices in your pocket. At the center of the Great Green Transition lie critical minerals such as lithium, nickel, cobalt, manganese, and rare earth elements. These metals power electric vehicles, solar panels, wind turbines, and energy storage systems. Yet they are concentrated in a handful of nations. China dominates over 80% of refined rare earths. Production Australia and Chile account for more than half of global lithium output, while the Democratic Republic of the Congo supplies 70% of the world's cobalt. Meanwhile, the United States struggles to permit new mines with environmental assessments that can stretch over a decade. What we end up with is a paradoxical situation in which the green technologies promising a carbon-neutral future rely on mining operations in some of the world's most unstable regions, and on processing facilities thousands of miles away that can be shut off at the turn of a political screw. When China tightened export quotas on high-performance magnets in mid-2025, automakers warned of production halts because electric motors rely on neodymium and dysprosium magnets, turning ambitious clean energy targets into a race against time. The technological battlefield extends far beyond minerals. Semiconductors underlie almost every strategic sector, from fifth-generation networks to artificial intelligence to guided weapons. Yet over 70% of advanced chips are manufactured by two foundries in Taiwan and South Korea. Setting up a single fabrication plant can cost upwards of $15 billion and take 3 years to construct. Then years more to train operators for next-generation, extreme ultraviolet lithography tools. So even as the United States pours more than $50 billion into domestic chip subsidies, it finds itself in a race not just to build factories, but to build expertise and build diplomatic shields around equipment exports to prevent a single adversary from strangling the supply chain. Digital infrastructure reveals another dimension of strategic vulnerability. Data centers require vast amounts of power and advanced cooling systems. Fiber optic cables snake across landscapes and under oceans, connecting billions of people. Yet they can be severed by natural disasters or undersea sabotage, creating blackouts in communication, financial transactions, and emergency services. China's Belt and Road Initiative has invested over $200 billion in ports, power stations, and digital corridors across Asia, Africa, and Europe, forging dependencies through infrastructure that can translate into political leverage. What happens when a key submarine cable is cut and remote work grinds to a halt? How resilient is the global internet when it rests on fragile lifelines? In addition to subsea cables, the reliance on single points of failure extends to undersea data hubs under concentration in places like Mumbai and Singapore, and to satellite constellations managed by a handful of nations that control orbital slots. In 2024, a malfunction in a major Earth observation satellite temporarily disrupted weather forecasting models across Europe, illustrating that space has become as contested and critical as seabed infrastructure. In the defense realm, the stakes could not be higher. The modern battlefield depends on hypersonic missiles, drone swarms, satellite networks, and cyber-enabled electronic warfare platforms. All of these systems rely on advanced materials such as high-purity nickel, cobalt alloys, rare isotopes for next-generation reactors, and radar-absorbing composite polymers. Sourcing these materials requires precision manufacturing and complex global supply chains. America's push to onshore defense industries collides with economic realities. Private firms balk at high costs and low returns, while allies worry that over-aggressive reshoring could fracture long-standing partnerships. For instance, The U.S. Navy OSOS efforts to produce domestic titanium alloys for shipbuilding has been beset by cost overruns and delays, prompting concerns that lack of competitive pricing may force continued reliance on imports from allied nations. So where do we go from here? The future will bring more fragmentation as governments exert direct control through subsidies, stockpiling, export controls, and strategic partnerships, creating blocks of friendshoring where like-minded nations pool resources and technologies. We may see the European Union and United States align critical mineral policies, establishing a common strategic reserve of lithium, cobalt, and heavy rare earths, while India, Japan, and Australia form a semiconductor security pact to diversify chip production and shield vital equipment exports from coercion. Latin American countries could band together under a critical minerals alliance to share refining capacity and negotiate better terms with buyers. At the same time, innovation in recycling and alternative materials offers a glimmer of hope. Recycling rates for rare earths hover below 5% today. Yet advancing chemical and biological recycling processes could reclaim 30% of rare earth elements from electronic waste within a decade. Imagine a world where retired wind turbine blades and spent smartphone magnet coils feed next-generation clean technologies, where municipal recycling centers host specialist extraction plants, and where micro-factories using green solvents process magnets, locally reducing transport risks. Small modular reactors could provide low-carbon baseload power to remote data centers and off-grid communities within 10 years, while sodium-ion batteries could offer a lower-cost alternative to lithium-ion for stationary grid storage, with reduced fire risk and greater life-cycle sustainability. Yet these breakthroughs require sustained research funding, public-private partnerships, and global collaboration to scale innovations from the lab to the factory. Without strategic coordination, isolated efforts will leave gaps that rivals will exploit, and vulnerabilities will persist. Consider the example of graphite, essential for anodes in lithium-ion batteries. Over the past 20 years, China has consolidated approximately 75% of spherical graphite production, while new mines in Africa and North America have struggled to secure investment and environmental approval, leaving processors dependent on Chinese processing technologists. The lesson is clear. Unlocking resilience demands a multi-tiered approach that combines diversified sourcing, jurisdictional risk assessment, capacity building in emerging producer countries, investment in next-generation processing methods, and robust governance frameworks to ensure environmental and social responsibility. At the consumer level, these dynamics translate into your morning coffee machine powered by electricity generated from wind farms on the Texas plains, your smartphone containing magnets refined in China and batteries assembled in South Korea, your video call streaming through undersea cables laid by European telecom firms, and satellites launched by SpaceX, all interconnected, yet controlled by a complex web of geopolitical interests. Failing to grasp these hidden connections leaves you vulnerable to sudden price shocks, supply disruptions, and strategic coercion. Understanding the interplay of energy policy, tech, investment, industrial strategy, and geopolitical power matters not just to CEOs and policymakers, but to every citizen, because the security of your data, the cost of your electricity, and the integrity of your national defense depend on these invisible threads weaving through politics, markets, technology, and nature. As we navigate an era defined by rapid technological change and climate imperatives, the choice is not between globalism and isolationism, but between strategic coordination and reactive scrambling. We must build resilient alliances, transparent supply networks, and adaptive regulatory systems that can respond swiftly to crises and foster innovation without sacrificing sustainability. The challenge is immense, yet the opportunity is unprecedented. We stand at a crossroads where decisions made today about subsidies, export controls, stockpiles, recycling standards, and research priorities will shape the geopolitical contours of the 21st century. Economy, security, and environment are no longer separate spheres, but facets of the same global struggle for power, influence, and survival. And if this exploration through the dizzying currents of global geopolitics has shed light on the forces shaping your world, consider giving this video a like and subscribing for more insights. Let us navigate these turbulent waters together so you are never left wondering what comes next.